motivation from one dimension, we can try to formulate the definition of the derivative of the scalar value function. So let's recall, let's begin with the definition, the conclusion of the things that we did last time. So we said that imagine if I have a function f where the domain, so it's a scalar value function x where u is a subset of Rn and is open, okay? Then the linear approximation this linearity we will verify later. Actually, it's indeed linear approximation. Okay. Then this f is differentiable at a point A in U. Okay. If we can find a good linear approximation, a good linear approximation where limit norm of h goes to 0, f L A h must also depend on A and h, and the norm of h goes to 0. So that's what is really the precise definition of the Frechet derivative actually. Okay, so there which is early, we call it here, we may denote L to be the derivative of the function f at the point A. And that will be basically a transformation from Rn to R. Okay. So this L displays the role of the derivative, something that you like that. Okay. So once again, so if I have a scalar valued function, okay, so it's taking inputs from an open subset of Rn, then we say that f is differentiable at a point, shall it be at a domain, okay, that's a different domain, if there exists a good linear approximation, and by good linear approximation you mean that you have an operator L such that it satisfies this equality, okay, where we know, in other words, the increments of f can be approximated by something linear, okay, plus the error. So if I remove it, then this increment is approximately linear actually. But if I add error to it, then you have equality. Okay, and this error is basically kind of an error which satisfies this limit actually. And we interpreted this limit last time, and we said that this means that the error is going faster to 0 than the denominator h actually. So it's rapidly going to 0 as compared to the h as as norm of h goes to 0 actually. Okay? So if this is happening, then you will call this L as a good linear approximation to the increment. Okay? And this linear approximation is basically your required derivative. Okay? So we talked about all this stuff in detail yesterday. Okay? And what? So let's do some examples. So let's see that how does it work. So we did one example, so we're going to do some more examples as well. No, it should be R into R. Yes. Okay, when you have higher dimension, then you can have it. Why? Because think about it. This is a number. That's a number. F is a map from U to R. So if you are evaluating F at point A plus H, so this is a number. This is a number. So the difference is a number. So you should have number on the other side. Okay, so this is a number. So L of H should be a number actually. So it's a map from R into R, but we will show later that it's a linear map actually. Okay. So it's not only linear in the sense of the linear actually, but it's indeed a linear transformation actually. So the derivative, as we also know, from our single variable calculus stuff, that the derivative is a linear transformation. It's a linear map. Why the derivative is a linear map? Because we know that derivative of the sum of two functions is the sum of the derivatives actually. Okay? And the derivative of a scaled function, in other words, a number multiplied by a function is same as that number multiplied by the derivative of the function. So it has those two crucial properties actually. Okay, so let's talk about some examples. Okay, so this derivative, so I also talked yesterday that we gave it a name, the Frechet derivative, because the Frechet was a guy. Okay, engineers like to call it total derivative actually. Okay, so it has both names. Okay. So let's take a linear polynomial. So here's an example. So let's take a map, say, of x1, x2. So f, take a map from f, which is a map from Rn to R, and define it by f of x1, x2, and xn equal to c1, x1 plus c2, x2 plus 1, and so forth, cn and xn. Okay? So it's a linear polynomial actually. Every linear polynomial is also a linear transformation. Can we see how easily? So if I keep this as an abstract vector x, so if I said that x is this x1 up to xn, and I define a vector c to be c1 up to cn, then I can rewrite about definition as f of x equal to c dot product with x. So c dotted with x. That's what is the meaning of it. So what is our objective? So we would like to have, we would like to compute the Frechet derivative of such a linear map. So in order to compute the Frechet derivative, what we need to do, I need to compute the increment. So let's compute, say, f of a plus h and compute f of a. Okay, so if you compute it, what you're going to get? So the output would be c dot a plus h minus c dot a, okay, which turns out to be c dot a plus c dot h, and c dot a will get cancelled, and you're going to have c dot h plus nothing. Okay. So if I compare it with the definition, okay. So the definition says that whenever you will compute the increment, you should see the two parts actually. Okay. So the one part that purely depends on h, and one part that depends on a and h actually, the point. Okay. So when I see this, okay, so I can only see the thing that depends on h. So there is nothing which depends on a actually. So the question is, what is my linear approximation here? So I will treat this guy as my L of h. Okay. So this is the L of h. And what is error actually? Zero. So error is 0. So what I need to do, I need to take f of a plus h. Okay. So define df of a as a map from Rn to R by that whenever df of a mapped onto df of a or L, it doesn't matter. So whenever df of a is mapped onto some h, it gives me what? So I want to give this definition to it. So c dot h actually. Okay, and the error is what? EF L A H, and this guy is 0. So does this, your error should satisfy this condition actually. So if the error is 0, okay, and if I divide it by norm of h and take limit norm of h goes to 0, so this guy would go to 0 actually. Okay. So you can say rightly, or maybe when I'm writing this is par aap aitraz karte hain, so you may ask that, okay, why I am giving it the name derivative. So derivative to abhi sabit nahi hua. Derivative, so this I must give it a name L at the moment. I should say L of h is c dot h. I can call this L derivative if this is true. So if this is not true, the L would not be derivative. So it's better to call it L as it is. But now, since I know that error goes faster than the norm of h to the 0, so this L is my, what do you call, Frechet derivative. But here is something very interesting actually. Okay? So the Frechet derivative for me operated onto h is what? This c dot h actually. But c dot h can also be treated as, think about it, f of h actually. In it. Because this is what the definition of f of h is. So in other words, the Frechet derivative at each h and f at each at h agree with each other. So if they agree with each other, you can say, so what can I say? That the Frechet derivative of the linear function evaluated at a is itself. So whenever you have a linear function, okay, and you want to compute this Frechet derivative or a total derivative, it would be itself actually. Okay? So, and this makes sense, we discussed it last time as well, that f is already linear. So if something is linear, what is the best approximation to that linearity? So you're going to call it itself. So you don't need anything else. Okay? You don't need, so if something is linear, the best or the good approximation to it would be, itself actually. So it makes sense to say that the derivative of f of a is
टर्म्स आपने भी बताया इसके बाद
हाँ
अभी एरर भी होती है तो अभी सुबह के टाइम डिफरेंशियल डेरिवेटिव थे.
So let's do another example and we'll see. So now let's see. So this was a pretty trivial example. Now let's see the example. One of the consequences of this definition is that in other words, imagine you have this function f of x y equal to 2x plus 3y, and I am asking what is the derivative of it, Frechet derivative or total derivative of it actually. So you're going to say itself. It would be itself. So the derivative of this function at any time a, operated onto some h or maybe x y, doesn't matter. So it would be equal to f of x y itself, right? So every linear thing has the same derivative. Okay. Now let's come to a more non-trivial example. Okay, where you have this. So let's take f of x y to be something non-linear. So you have this x y. Okay, and let's try to compute its derivative at any point that we like. Okay. By the way, maybe a remark would be, and if you see definition, so the definition says that you compute increment and you're going to get L of h plus error. So the error, so I can write that f of a plus h minus f of a minus L of h is what do you call error. So if I take absolute of it, there is no difference in taking absolute because the sign is not important. The important is that what is the difference, how this guy is different from this actually. And divide everything by norm of h and take limit. Limit norm of h goes to 0 and take limit norm of h goes to 0. If this goes to 0, then this L is the derivative, the Frechet derivative of it actually. Okay? So if you wish, you can keep that definition, but the equivalent condition would be, you can have this as well actually, that okay, compute f of a plus f of a plus h and f of a, subtract your potential L of h and divide it by the norm of h and see whatever is remaining goes to 0 as norm of h goes to 0 or not. So if it goes to 0, L is the derivative. So let's think about from this perspective. Okay? So let's take f of a plus h. So take a to be a vector a1, a2 and h to be a point x2. So f of a plus h minus f of a would be what? So this is going to be f of a1 plus h1 and a2 plus h2. You must be thinking, why computation of this derivative is difficult actually? We know one dimension we can calculate like that actually. Why this is like that? You will see that, so once you understand the definition, we will create a cool shortcut actually of finding the derivative like that. You don't have to do all this stuff to do it. But obviously, you also have to learn to do things by definition. So you have it minus f of a1, a2. Okay? So what will be the outcome of the first quantity? So you're going to have a1 plus h1 times a2 plus h2 and minus a1, a2. Right? And then you have a1, a2, a1, h1, a1, a2, h2 plus h1, h2 and minus a1, a2, right? So this gets rid of it and you are remaining with three things actually. And now think about it. So from this expression you have to kind of guess actually that which thing should I give name. वो ये कहता है take this as the error FAH, ठीक है, and take this as the derivative. ठीक है? In other words, the derivative would be a1 h1 plus a2 h2, and this means that this is going to be h1 h2 over norm of h1 square plus h2 square. So that's how it should be. So in other words, you have to be careful that, in other words, okay, would limit exist if I take a1 h2 and a2 h1 here actually? I think you would have already felt the sense that maybe you are getting something, you know. But have we done, you know, this problem xy over the square root of x square plus y square? I think limit for such function should exist. You must verify this. You must verify that this must be true. Okay? So the derivative must be this. Anyway, so in other words, out of these two expressions, you have to think carefully that when you divide by the norm of h, which thing will go to 0? So choose that as error actually. Okay? Choose that as error rather than doing other. Okay? But when we'll see, for example, you know, how to quickly compute such kind of derivatives, okay? We will basically, you can counter check your, you know, way through that as well. So, in other words, when you are computing derivative, you should have a intuitive answer in front of you that possibly this is going to be the derivative. Anyway, so my point is this: I computed increment, so I have two things with me, and I have to carefully decide which of expression should I call derivative and which should I call as the error actually. Okay. आ जाएगी।
ये नाम सर एच के टर्म में ले रहे हैं यहाँ पर एरर सर।
नहीं।
सर हमको एरर ए और एच दोनों इसमें दो एरर होती है ना।
A और H होना चाहिए in principle, but you have to think actually that okay, if you are taking this as error, okay, so not everything that I say is a hard and fast rule.
Yes.
You have to be careful. You have to counter check. I can say sometimes dumb things, so don't worry about it. Anyway, so in other words, you have to make sure that whatever you are, you know, keeping something as error, when divided by norm of it, that should go to 0. If it is not going, you have chosen something incorrect. If it is going, maybe that would be a good answer. Now maybe you can ask the question that, you know, what if the both goes to 0? Dividing by the norm of h, then what would be the, you know, kind of a thing? Then